All right, hello everyone. We're here in my office in front of a live recording audience. Yeah, they're pumped about physics, as I'm sure you are.
Yes, yes.
Yeah, I'm guessing you could guess who that is. But anyway, we're gonna do some problem solving on the last of the Wiley plus problems, number 56 from chapter 6. It's a pretty tricky one, all right, because we're really only given a couple things. We're told that you have a car that's driving on a highway. The highway is designed to allow the car to move at 63 kilometers an hour with a curve radius of 209 meters. In my problem, your numbers are probably different. And it's asking you what is happening, what coefficient of friction is needed if traffic is slowed and you're only moving at 45 kilometers per hour. So the first thing to understand is at 63 kilometers per hour, so at 63, we're told that that's what the road is designed for. It's designed so that it can make the turn with zero friction between the car and the tires, right? And so we've seen this in class a little bit, but if we look at our picture here, I'm going to label my axes. You have two options. You can either label them in this manner, where this is your x and this is your y, or you can label them using what I'll call, I guess, the blue axes like this, where this is your x and this is your y. Okay, so it really depends on the situation. I'm actually going to use both axes. I'm going to use the blue ones initially and then the red ones later on. So my inclination is to jump into the problem solving process and figure out the coefficient just starting at 45 kilometers per hour. But what I would find, and you would find it if you jumped into it yourself, is you do not know the angle of the ramp that I'm going to label theta. And so you would not make it very far in solving for the coefficient of friction at 45 kilometers an hour without knowing the angle. So I'm going to use the information they give us at the beginning, this 63 kilometers per hour, and the blue axes to determine what my angle is, and then use that to solve for the coefficient of friction. So let's do a free body diagram here. I'm going to pick a different color since I have these different color axes. I'll go green. All right, so my free body diagram, what forces do I have? Well, I'm on Earth, so I know I have my weight going straight down. All right, I have a normal force going up, force normal, perpendicular to the ramp. And for the first portion, since the road is designed so that you can rely on zero friction, for the first part, those are my only two forces. And then just to make a note, I'm going to tell myself or remind myself that I do have an acceleration, and it's in towards the center of the track, right? So I'm going to have my acceleration in this direction. It's not a force, the acceleration is just the acceleration, so I'm putting it separate off to the side. So for part A, if I wanted to set up the sum of my forces, I'm going to use the blue axes. All right, so using the blue axes, if I do sum of the forces in the x direction, they'll be equal to 0 because we want to, oh, just kidding, they're not equal to 0. Haha, got you. Okay. Sum of the forces in the x direction should be equal to ma, where a is our centripetal acceleration, because if you look here, this acceleration is completely in the x direction for the blue axes. So sum of the forces equals ma, and then sum of the forces in the y direction, those are equal to 0. So if we look at our free body diagram, in the x direction, the only force we have is a component of the normal force. Again, we're using the blue axes, so the normal force is theta degrees rotated away from the y-axis. So maybe over here off to the side, maybe I'll break my normal force into x and y components. So the normal force in the x, looking at that picture I just drew, would be the normal force. It's the opposite side, so times the sine of that angle, theta. And then the normal force in the y direction will be equal to the normal force multiplied by the cosine of that angle, theta. Okay? So, if we come over, looking at some of the forces in the x direction, the only force we have in the x direction is the normal force multiplied by the sine of theta, and that's going to be equal to m times a centripetal. What's a centripetal equal to?
Oh, velocity squared over radius.
Perfect, good. So v squared over our radius r. Good job. Matt's thankful that he got bailed out. Sorry, is that okay? But as you can see, we don't know the normal force, so we can't solve for the angle theta without knowing the normal force. So let's go over to our sum of the forces in the y. In the y direction, we have the normal force times the cosine of the angle theta minus mg equals 0. Right? So it's a little sloppy, but you can solve normal force algebraically will just be equal to mg, the weight, over the cosine of the angle theta. So if you plug that in, over in this equation here, we have mg over the cosine of the angle theta times the sine of the angle theta equals mv squared over r. Our m's cancel. Sine over cosine is tangent. And then we can divide by the g. And so what we find is that the tangent of our angle theta is just equal to, oh, that's a sloppy looking v, I'll erase that, is just equal to v squared divided by rg. So right there, boom, you can solve for the angle theta. And I think this equation might even be in the textbook, I'm not sure off the top of my head, I think it is somewhere. But if you didn't see it there, that's fine, you now know. Cool, so that was fun. That's all good for just figuring out our angle theta. Now we can actually start to solve the problem. So to solve the problem, the remainder of the problem, I've decided that I want to look at the red axes. And so I'm going to come down here, maybe I'll redraw a new set of axes. Maybe I'll just give us a blank slate here because it's getting a little crowded. So let's redraw our free body diagram. All right. So this is y, I'm calling this x, all right, and our forces now, we have our normal force up here. Oh, just kidding, that's not the direction of our normal force. Normal force is perpendicular to the ramp, so the normal force should be entirely in the y direction, right? So the normal force should be here. The weight force is straight down, and now we're going at a speed that's slower than the suggested speed. Okay, so we're going to have friction, and the question is, what direction is that friction acting?
It will be parallel to the ramp, but up.
Oh, nice, good job. So the reason we know, first of all, we know it's parallel to the ramp because friction is always parallel to the surface of contact, and we know that it's up the ramp because we're going below the suggested speed. So again, we would have a tendency to slide down the ramp, and so we need friction to keep us from sliding down that ramp. And just again, as a reminder, maybe over here I'll draw our acceleration is off in this direction, and so what you're going to find is that the acceleration is also now going to have x and y components. So I'm going to draw another little coordinate axis there. So just to clarify, so that we understand our angles, this here is our angle theta, the angle of the ramp that we just found earlier, and similarly, this angle here, by I think alternate interior angles, should also be found to be the angle theta. Okay, so before we start solving too much, we're going to be doing some of our forces, but we need to break things down into their components. Right? So our acceleration, for example, is going to have an x component. As you can see from the picture, that's going to be this side here. So that will be a multiplied by the cosine of our angle theta. And our acceleration will also have a y component, which will be a sine theta. Similarly, our weight here needs to be broken down into components. So we're going to have weight in the x direction, which will be mg times the sine of the angle theta, and we're going to have weight in the y direction, which will be mg cosine theta. Alright, and that's really down, so you could put a negative there if you want. Alright, so now if we want to do some of our forces, alright, we can observe that some of the forces in this new x direction, the red x direction, will be equal to m times ax, and some of the forces in the y will be equal to m times ay. okay, this is all fun and good, right? I'm going to work from this here in a second, but what are we trying to do? What are we even trying to find? Remind me what we're trying to find?
The coefficient of friction.
The coefficient of friction, right? And we're trying to see what its minimum value is, right, to just prevent us from slipping. So to prevent from slipping, we want static, which is why you can see up here I did a subscript S on my friction, all right? And if it's minimum, then we're saying that our friction must be equal to, if you don't recall, force of static friction is equal to mu S times the normal force. So if we're trying to find mu S, okay, I'm going to rewrite that. That looks like some weird different letter. Anyway, mu S should be equal to the force of static friction divided by the force normal. So if we can solve for those two and then just divide them by each other, we should be good. Okay, so now that's why I'm doing some of the forces, to try to find Fs and Fn. So if we look at some of the forces in the x, we come up here. I called down the positive x direction. So in the positive x direction, I have Wx, which is mg sine theta. In the negative x, I have my force of static friction, so minus the force of static friction. This is a tough problem. This is fun. Okay, is equal to mass times ax, which we can see up here is a times the cosine of theta. All right, so I can solve this for Fs. I'm going to rewrite this. Fs equals mg sine theta minus ma cosine theta. All right, that sounds good. And just to remind ourselves, what is a equal to again? V squared over r, just like we mentioned earlier.
Oh.
All right, because now we have a different v but the same r, so we need to keep that in mind. We'll plug that in at some point. So we have our force of static friction. I'm going to have to, well, yeah, I'm going to have to slide up to create more room. Sorry about hiding our free body diagram. So that's the x direction. Now if you do the sum of the forces in the y, what we have in the y direction, in the positive, we had the normal force. In the negative, we had the negative component of gravity, which is mg cosine theta, and that was equal to m times ay, which was a sine theta. And so now we can solve for normal force. It's just going to be equal to mg cosine theta plus ma sine theta. Boy howdy, huh? Okay, so now if you look, we said earlier mu is equal to static friction divided by normal. There's the static friction, there's the normal. So maybe I'll just write this out one more step just to make sure we're all on the same page. Maybe I'll go back to green just for kicks. So mu s is going to be this big ugly equation where you have the static friction, this whole thing. So mg sine theta minus ma, which we just said was v squared over r, times the cosine of theta, divided by the normal force, which is this whole thing, mg cosine theta plus ma, which was v squared over r, times the sine of theta. So you can reduce this. I see there's m in every term, so the m's can cancel. Sines and cosines don't, though, so that's pretty much what you would plug in, and that would give you what I think would be the green box of joy. So, good luck. Hopefully that is helpful. Oh, look at that. The crowd goes wild.
This is awesome!
Yeah.
Black smoothie!
Yes. Couldn't have said it better myself. So, anyway, I'll just do this. Yay. Anyway, all right. So, enjoy. Let me know if you guys have any questions.